following up the work that was mentioned before, I will, as University of Patras, we tried to develop some methodologies involving deep learning methods to for diagnostic and prognostic use. So in order to do this, we followed up the case study that was discussed earlier. Okay. So yeah, let's just go to the to the flow chart. So the experiment was described before extensively, so there is no point on repeating the description. So I will continue that in this case study, we exploited only strain data. As Mr. Galanopoulos described before. So we took the strain data and we had to pre-process them to be ready to be fed in the deep learning pipeline. Also, in this figure, you can see the target value, which is the stiffness reduction, if we speak for a diagnostic model, or it can be a remain useful life target if we speak for prognostics. Then we pass this pair of data to a deep learning algorithm, where as input are some strain health indicators, and as output is the stiffness for diagnostic or the remaining useful life for prognostics. And then we obtain results like the one that you can see on these figures, where at the left are the stiffness assessment, and on the right is the remaining useful life prediction. So let's go more in detail. From this experiment, we had available 5 FOD panels. The FBGs were not always 16 sensors. Only FOD3 had less sensors. So we concluded that we will take it out from this modeling. So we used only FOD4 until FOD7, which had 16 sensors, and you will understand why we did that later. And this is the process of the pre-processing. Because the FBGs were capturing strains through all the experiment. This is a very dense information, and in order to reduce the dimensionality and reduce the overflow, the data overflow of the model, we had to reduce it. So we used the 200-second windows, and we averaged the mean value from them. And then we applied a rolling window just to smooth out the data. Some ordinary dropping non-values procedures. And then I want to talk about a little bit of the intuition behind how we developed this health indicator. Okay, so as George said before, the strain are heavily coupled with a load. So by seeing only strain, you cannot see the damage inside the strain because you see also the load. So we needed, and also these experiments, because the load is not constant, but it's increasing as the time increases. We had to rethink the approach differently. So we had to find a way to decouple the load from the strain. So by observing these plots, someone can see that where after the half part of the experiment over, where the damage is has progressed and the damage is more severe, someone can see that the slopes of some sensors start to diverge. So the intuition was that we will use the strain slopes, the first derivative of strain, and not the raw strain. So we calculate the first derivative of the strain, and then we accumulate it by summing over the strains over time. And this was the health indicator. Yeah, this is briefly what I just discussed. And then these plots, you can see the difference between different pair of sensors, and especially their strain slope. So you can see that at first there is not much difference because there is no damage or non-linearities. The slope is changing with the same rate for each sensor. But at the second part of the plots, you can see that there is exponential behavior that indicates that one of the two sensors is starting to deviate. So this is probably a damage indication, but for sure it's a non-linear indication, which is not something good. So this gives us a very good indication that something bad is happening to the material. So because we had 16 sensors, and if you take all the possible combinations between pair of the 16 sensors, it's a lot. And so we had to think of a different approach of a neural network that can take advantage of all these pair of sensors and how they communicate with each other. Because if we just put every pair of sensor as a feature in a big tensor to fit the neural network, we will exclude some internal information that could be transferred between different pair of sensors. So we had to think of something different. And this architecture, this model, the graph neural network, is appropriate for such modeling. So in the graph neural network, each node of the graph can represent a specific strain sensors. So in our example, we had 16 strain sensors. As you can see, we have 16 nodes, and this plays the role of a community. Like you have 16 sensors that they form a community, and they can communicate with each other. And we fed this network with pairs of strain, the health indicator values that I explained before, and stiffness or remain useful life values. So we convert the problem to a regression task, and particularly a graph regression task, where imagine that in each time step, the state of the graph neural network at that particular time step is mapped to a specific value, either a stiffness value, either a remain useful life value. Many of you maybe know this kind of neural network that is used in social networks like Facebook, or for molecular structures that have a spatial formation. And some brief overview of what is a graph neural network. You have an input layer that you pass the data. You can put some traditional MLP layers to act like an embedding layer, so they can transform the information from the input to meaningful information that the graph neural network can use. And then you have the graph neural network, which inside of the graph neural network, you have many other neural networks. In this case, we used the graph convolutional network, which communicates between nodes and aggregates the message between the nodes of the graph neural network. And after you do this processing with the graph neural network, then you output the values, the message that the graph neural network has learned. This information, you aggregate it again, using a global pooling layer to aggregate all this information, and then you use traditional MLP layers, fully connected multi-perceptron layers, to guide the information until the desired output value. So, because we had only 4 specimens, 4 panels, we applied the k-fold cross-validation method, where in each training cycle, we left one panel outside to be unseen from the network, and then we validate and calculate some metrics like mean square error, root mean square error, and map using this unseen validation set. So you can see that the network is capable, is robust. It can capture with great accuracy and minimum errors the stiffness. It is important to notice that FOD5 was the only panel that damage had not been introduced. So it started as a healthy panel. Instead, the others had some damage inflicted in form of impact. So as you see, FOD5, the prediction is underestimating the true stiffness values. And this is because in the case of FOD5, the model has been trained with panels that damage was imminent. So so this model knows to predict more conservative, because it has only seen damage in his life. So when he sees something healthy, it's very normal to underestimate it. But you can see the underestimation is not very bad. it follows the trend of the stiffness. Okay. And then we did some training with for prognostics, predicting the estimation of the remaining useful life of these panels. As you can see, yeah, the remaining useful life prediction is also very good. With the black arrows, we have pointed out the stiffness reduction point, so it can be easily translated and compared to the stiffness reduction. Again, the metrics are very good. And one by one comparison of stiffness and RUL prediction. This is the hyperparameters that were used. We used I don't know if I should go in much detail here. This can be asked after in a Q&A. Okay, and then I will describe the guided wave approach using guided waves. So as you can see, we have the red dots represent the guided wave acquisition that was done at the certain cycles of the experiment. So also we will focus only on the 4 actuators of the 4 sensors, not the printed one, just the PZT ones. And as you can see, the experiments were done for many different frequencies, and for each frequency, we had 1 actuator excites and the 3 receiving. So we had 4 actuator combinations, and then for each of these combinations, we had 10 repetitions. So at the end, for each FOD panel, we have 200 signals for each red point in the graph. So this is very good, a lot of data, and it's and with this amount of data enables us to perform a variety of deep neural network approaches. And we haven't yet finished running the models, but we already know how we will approach this. We will insert each of these 200 signals for each point. We insert this through some convolutional layers in order to extract meaningful features. And then each of these we will map with the stiffness value or the remaining useful life value in the same approach that was done for strain. So as we can see, using graph deep learning neural network, it's a very capable and astonishing architecture that capturing the unseen data, even in our case that we had only 4 FOD panels available. Also, the intuition behind that we need to decouple the load, and by that introducing the new health indicator that is the slope difference of the strains, tends to be a very good approach. And of course, this pipeline can be implemented online in real time to to infer. Okay, yeah, the training was stable. We are not in the overfitting regime, but we are in underfitting. So it's generalizing efficiently. Some future plans, because with so many data, there are a lot of options, and there are a lot of good ideas that can be performed, and meaningful results can be taken out from this. Some future plan is to reduce the combination of sensors that can be used in the graph neural network. For example, we can use 6 sensors instead of the 16. And by that, we can also include the 43, which had 6 sensors, and examine if smaller combination of sensors can give the same or close to same results. Also, this is an inherent advantage of the graph neural networks. Someone can put more information in the graph neural networks as edge features. We didn't did that for benchmarking reasons. We went with the simplest case, but you could someone could put the coordinates of each sensor as edge features, so you can teach the model to learn the Euclidean distances of each sensor, and maybe it can be easier to generalize this neural network to a different sensor setup. Then we would like to attempt the transfer learning methodology to use similar but different specimens, which have also similar FPG arrangement, and train the network on this arrangement, and then do one-shot prediction to see how the same neural network can perform in a different kind of dataset. Also, we made in our graph neural network, we made all the nodes to be connected with all the other nodes. So all the strain sensors were connected with each other. But the graph neural network leaves you the opportunity and gives you the choice to leave this arbitrary. So it can you can leave all the connections unknown and let the model learn the connection between sensors. So what we mean by that is, like, you imagine that some sensors, they make some neighboring communities. They are more relevant in specific regions than each other. So imagine like there are trees of sensor communities and not a full connected community. So there are a lot of opportunities and that can be explored by following this direction.
Thank you.
Thank you for your attention.
Thank you very much, Giannis, for this presentation of this valuable work. Thank you.